quiz time at the beginning. So just to ask you the questions. What are the 3 elements in the creep failure? So anyone can answer these questions. You can unmute yourself and say it loud. Okay. Anyone? Seems no. So let me just see what's happened here. Oh, someone is typing. Yeah. Temperature, time, and load. Excellent. I hope you can say it loud, but if you don't want to say it out, speak it out, I can help you. Yeah, that's good. So that's the 3 elements: temperature, load, and time. And if we do a creep test, normally we can do that either at constant load or constant displacement. So in this case, we talk about doing this creep test at constant load at elevated temperature for a certain amount of time. So like this. Okay, I'm heating up the material and apply a load here. And so when you look at the creep strain curve, which is plot strain against time, and basically you can see it is starting from a instantaneous elastic strain here, because that is from the elastic deformation. And after that, after you keep this load for a certain amount of time, then this material will kind of deform, elongated in this direction. And you can see the creep strain is growing at the beginning a bit quick and then come to a place which is like a plateau, but this plateau is not flat one. It has a linear relationship. Basically, it looks like a linear line. Okay, so this is called the secondary regime after this primary regime, and then you can look at this gradient, which is the derivative of time d epsilon dt. Okay, that give you strain rate. And then if you keep the load for a very long time, eventually it will reach this third regime, tertiary regime, and then it will fail because the material is thin too much and there's some kind of void becomes so huge, like a big void, eventually connect each other and break your sample. Okay, I think someone is raising the hand, so let me come out of that. Okay. Yeah. I'm recording these things. I'm already doing that, so don't worry. You can always go back and watch it. Okay. So let's continue. And we finished that. Let's go to this one. So this is basically a summary of the creep curves from the beginning primary creep, and this is basically the strain hardening. Eventually, the strain hardening will give you this kind of tail off part because the material become stronger as the strain goes. Strain hardening, basically, if you have a strain, stress and strain, and you go linear region and then go up and keep hardening. Okay, that kind of behavior will correlate to your this creep curve, okay, and then you will have a linear plateau. They are plotting different things, but here is causing by this strain hardening effect. Okay, I'm sorry for this pain. It's not really handy. And second creep, that's the most important part. Normally we call it steady state creep. And later on we will describe the creep mechanism, which is also most of the time talking about this regime. Okay. And tertiary creep, which is a rapid area, you increase your creep strain rate and eventually fail your samples here like this, which we call creep rupture. Okay, so what happens if we do creep tests at different stress or temperature? So for instance, you increase the stress or temperature in this curve, you can see, for example, increase the stress basically means the material are under very high load and they will fail much earlier than it should be. So you can see the strain rate is increasing if you look at the gradient of each line here, okay? And it will fail eventually like this. So both will push the curve to the left, okay? Either increase stress or increase the temperature. The two important results from the creep curves. First thing is you need to work out the steady state creep strain rate and also work out the time to failure so that you can predict the creep life of your engineering material. Okay, let's look at some example. For example, here. Okay, this is the equation which describes the steady state creep strain rate. I said very important. You need to remember the equation because actually, if you look at the equation, let's look at the equation one by one. This is the creep strain rate, okay? D epsilon dt. And this A is a constant. And now we see here, this is the stress you applied on your sample. And you can see there's a coefficient. That value normally is larger than 3, okay? So this means it's very sensitive to your stress. And now you can see a term which is an exponential function. And then in this exponential function, if you remember your thermodynamics course, you will see actually a very similar form like that. Q is the activation energy, okay? What that means is it's kind of an energy barrier for the material to resist the heat. So you need to raise the temperature high enough here. So temperature here, T, high enough to overcome this activation energy so that you will have a creep to happen. R here is the universal gas constant. So it's just a constant you'll be given. So remember, temperature here, we are talking about in Kelvin scale. Kelvin scale. So whenever you have a Celsius, you need to change that to Kelvin, which is 273 plus the temperature in Celsius, okay? And remember this equation, and this will be the most important part in creep. And this also has another name because there's a power here, N. So we will talk about the power law later on, okay? So this can be the equation for the power law creep, power law. And you can see from the bottom of this here, so it's kind of exponential dependence on the stress, that's the power n, and also it's dependent on the temperature. That's the only two things you need to remember here, stress and temperature. But what happens for the failure? So for the failure, normally you think about you have a failure strain. Okay. Let me go back. So failure strain normally is given. For example, for a metal 0.1, that's 10% of strain. So if you want to work out the time to failure, basically that is equal to the final failure divide to your strain rate, creep strain rate. Okay, so that looks like a kind of a length or displacement, and this looks like a velocity. Okay, this is the failure strain, and this is like the velocity for the material to deform and creep, and then that give you the time to failure. Okay, so that's the basic equation, how to relate it to that. Normally for the calculation you will be given the final failure strain measured and the normal temperature. Okay, probably not right, just correct myself. That final failure strain could be measured in high temperature, but they will give you that value. Okay, so I just want to say what happened for the secondary creep. Basically, it's a balance between deformation and diffusion-based recovery. I will approach the diffusion part later. So there's a lot of mechanism operating depending on the regime of the stress and the temperature that activate different deformation process. So experiments to predict the behavior normally at much lower strain rate because we want to understand what's happening. So these things are showing you later, last time. So engineering application, we don't want strain too much strain rate, I mean creep strain rate. So that will have a almost infinite life, several years, let's say several years. And if you're doing creep experiment, you will accelerate your creep rate so that you can measure something within months, okay, or days. But if you want to do some hot walking and really like make a sword or make some structure, you want to finish that within hours, okay, or minutes. So that's why you need to understand creep behavior, and so you can raise the temperature or raise your stress so that actually you reduce your time. Okay, that's the logic from this graph. So let's look at some experiments was done in and constant temperature, which basically at constant temperature T, and you vary the stress sigma. So you can see the strain rate basically is the power law relation. So a small amount of stress you increase will increase your strain rate very quickly. So that's why you see the curve here, strain against time will go from that way. Okay, so the slope here is increasing, representing the creep strain rate. If you do the log on this equation, like last time I have done for you, so basically this one log on both sides, this come to here, log strain rate. And if you remember, log AB equal to log A plus log B. Okay, so that gives you log A here. And there's another relation from, for example, log A with a power here will give you n log A. So A will come down. Okay, so by doing that, you actually take out the n to here in front of the log sigma. And because log is the natural logarithm, so that will basically log E is 1. Okay, so that will take out this one, and this term basically is the things here will come down to a constant here because temperature is a constant. So when you look at the equation, which one is the variable? Actually is this one, right? This part. Which let me rearrange the equation to here. So you find actually all these parts is constant. Okay, constant. And now you're plotting the equation log strain rate will be just a linear equation with the slope n, and this variable is log sigma. So now that's why you will see this curve, log strain rate plot against log sigma, which have this slope, okay, equal to n, which is this one here. And if you really want to calculate something, there's a intersection which give you the part here. Okay, let me drink some water. Okay, thank you. Now what happens if we do experiment at constant stress? So at constant stress, what happens, this one is constant and we raise temperature T. From this equation, actually, you can see if you raise your temperature, the curve will also go from right to left. The gradient here will also increase. So let's do similar things here. This is the exact same equation I did before, but the variable here now is t, time, and all this part is constant. So let's rearrange the equation, just make it more explicit. So you can see this part is constant, and 1 over t is actually the variables, and the log strain rate is the y-axis we want to plot. And you can see actually the slope is this part, activation energy over gas constant with a negative sign. So that's you can imagine the curve will be a shape like that. Okay, so when we plot curve, we plot 1 over t. So you can expect high temperature is here, low temperature is on the right, so that you can see if it is in high temperature, your strain rate is very quick. Okay, and vice versa in that case is very slow. That help us to understand the equation much better, right? So you can know the physical meaning of that. And let's do an example. This is the example which asks us to let's just example questions. So how much does the steady state creep strain rate change for nickel between 600 and 605 degree at constant stress? Okay, so this question is basically asks us if for nickel material, if it's under temperature 600 and we increase that to 605, what happens for the strain rates? How much changed from, so this should be a dot here, strain rate S1 to strain rate S2. Okay, so we are given the activation energy, this one. So it's Q is given. Be careful of this one, kilojoule more. Okay, normally I found someone who started the coursework already. He didn't consider this kilojoule. He just used 277. So in the end, the creep failure within hours, not years. So that's not right. Okay. And so we know this equation for the creep strain rate, as I shown here. And the first things I recommend everyone to do that is the easiest thing is to change your temperature from Celsius to Kelvin, which is T1 just plus 273, which give you this one. And T2 is similarly 878 here. And now you just substitute the equation with your given temperature. So you can find, I don't care what the parameter here, they are all constant because I'm apply a constant load here. So this question should mention we are applying constant load here. Okay, this is a constant load. So the stress will not change. And by substitute this temperature into here, okay, you get this equation. Similarly for this one, substitute that and the Q here, which is 277 times 10 to 3, okay, to here. And the gas constant is normally given, which is joule per mole per K, capital K here. So you get this answer. So now the question is asked how much that changed. But basically you can see this part can be cancelled out if we divide one over the other one. So let's do that. Epsilon S2 dot over epsilon S1 dot. Now give us value 1.24. So actually that's about 24% increase just by increase 5 degrees. You can see that's a very sensitive result. So you can imagine for creep test and the furnace, normally the furnace like your oven, you heat it up the things. The oven with a fan normally will reach a steady state temperature, but if you didn't control very well, it will have 5 degree variation, so that you will have a different creep strain rate. So actually, when you want to do a very accurate creep test, you need to make sure you can keep the temperature as a constant. Okay, that's what I said here. Very sensitive to temperature. And so you need excellent temperature control experiment. Okay, let's go to the second example. So second example here, which is here. Let me read the questions to you. The creep data in table 1, which is here, was obtained in the laboratory for high molecular weight polyethylene, that's a polymer material, at a stress of 5 megapascal. There's some questions. Okay, let me come out. Is A constant for the same material or for the same stress? Good questions. So A is a constant for, let me just, for the same material or for the same stress. Of course, for the same material, the A will be a constant. But here, when we talking about the question here, it means the A is the same for constant load, okay, constant stress, which is value here. And similarly for the N, the power here, okay. So let me, thank you for asking the question. Now let me go through the second example. We will have a break after this example, okay? So, like I said here, we apply a stress 5 megapascal, and the stress component N here for polyethylene is 1.3. It's very low. Oh, what's happened? Okay. Oh, you can see that. Okay, I think that automatically switch off. Let me just share my things again. Okay, now you can see it. Good. So let me open it. So basically, summarize the condition here. We apply stress 5 megapascal, and the power here N is 1.3. For polymer, is very small. Okay. So bearing surface of a replacement knee joint made from this polyethylene can tolerate a 10% of strain before being considered unserviceable. So what that means is final failure strain is 0.1. Okay, that's the condition. And the normal load on the polyethylene is 2 megapascal at 37 degree. That's your human temperature. I hope you didn't exceed this temperature at this moment. Okay, that's a joke. And the normal temperature on the polyethylene is that's the service life normally is 2 megapascal. That's not very high. And so the steady state creep rate is given here from the table at 70 degree. This value 1 10 to minus 3. So be careful of the unit here is per hour. Okay, so strain rate, normally strain rate, the unit you can say per second, or you can write second minus 1. Okay, but for this creep strain rates, we normally like to write per hour. Okay, so it's hour minus 1. So just be careful when doing the calculation. So I mentioned here, someone made mistake in the coursework as well. So the question is asking, calculate how many years of service life can be expected with the universal gas constant here. So let's move to the second page. So I put these conditions here as we found from the questions. For this table, all the data is measured when the stress is 5 megapascal. Okay, and so what the question we want to ask is, for the human body, if you use that knee, which normally under stress 2 megapascal at a temperature of 37 degree, how long you can use it? Okay, so that's good questions for the product. if you want to put that inside a human body, you would expect that can use for several years or 10 years, then you can replace it. Otherwise, that's really a painful surgery, right? Now, so to work out these questions, definitely you need the hint. The hint one is the equation for the creep strain rate, okay? And we know the critical value for the material to fail is 10% of strain. So let's work out how to do that. So the first things you can do is, like I said, temperature. Let's switch the temperature here, 70, 80, and 37 to the Kelvin. So let's say temperature 1 is equal to 70 plus 273. That's K. So that's 343 K. Okay? And T2, similarly, 80 degree is equal to 353 K. Okay? Just 10 degree higher. And the surface temperature TS is 37 degree, which is plus 273, which plus 273. Okay, that is 310. Okay, that's 310. 310K. Okay, correct me if I did something wrong. I think I'm right. Okay, 310K. Now, because you look at the equation here, let's just write this creep strain rate equation. You will see what you know is the, sorry, this is stress. This is not E, this is stress. What you know is this one for that table is 5 megapascal. And you can know that as well from the steady state creep strain rate. And you are given this temperature. The only thing you don't know, which is not given, is this coefficient A, and also the activation energy. So the second thing I would say is to find A, the constant, and Q, activation energy, which is for this special material here. Okay, let's go to step 2 to find A and Q. So basically, it's kind of solve an equation with 2 unknown. So that's why you need 2 equations. How we get that? We have 2 data, so we can solve it, right? So let's do it. Epsilon S1 dot give you this one, and stress is 5 megapascal. Let's just leave it. Let's just write stress. And EQ over RT1. Similarly, for the strain rate 2, we just basically copy the equation just by change the temperature. Okay, T2. So if you want to get the Q, the quickest thing I think here is to cancel all this out. Okay, so let's do that. Cancel that out by divide epsilon S1 over S2, which give you this EQ RT1 over E minus Q RT2. this can be simplified as, because for exponential function, that's a power function, basically you can simplify that by the top term minus the bottom part, which we can take out same things here, Q over R. And we found the only thing we can take out is T1, or 1 over T1, 1 over T2 bracket. Okay, so now things become a bit simpler. So we can do the ln, which is a logarithm on both sides, like ln here and ln here, which will cancel this out. Eventually we want to find the q, right? So let's do that. So ln on the left hand side will give us ln epsilon s1 dot minus ln epsilon s2 dot. And now we cancel this natural logarithm e. So give us q over 1 minus 1 over 1 t 1 over t2. Okay, so by doing that, we just rearrange the equation. We want to find the q, so eventually is basically r go to the left times r and go to the left. Now we get ln s1 minus ln s2 dot, and over these things. So we once this goes to left, and then you need to divide the whole term here. So let's do that. Because there's a minus sign, I just rearrange the equation. So t2 minus 1 over t1. So that's the equation for q. So I give you the final answer for here. Just be careful when you're doing the calculation. All the unit should be consistent. Okay. So now we get 151 kilojoule per mole. Okay. And normally, even in the exam, we tend to have you have 1 decimal point. So let's put 1 decimal point there. Okay. Now step 3. Oh, questions coming. Let's save it, keep it. Question comes. Let's see what's the question here. Can you sub the value in the equation, please? Good. Let's do that. So in case someone make mistake in this calculation. Okay. Let's do that. Where's my pen? It's here. So let's do that Q. So R is the value 8314, because that's the, let me write that the unit for R about here. R equal to 3 joule per mole. That will be given. Okay. Oh, 2 more questions. Let me come out.
Sir.
Yeah.
You know when it says Q equals to R ln S1 you have 1 over T2 minus 1 over T1.
Yes.
Just wondering, why did it change from the formula beforehand?
Just to answer your questions, because there is a minus sign on the right equation here. So the equation. Let me just go back to the slides. You can see. So to answer your questions, yeah, at the
Makes
beginning,
sense. Thank you.
yeah, there's a minus sign here. So I said I need to switch the sign. So that's the way I get that. Okay. So let's continue. So Q equal to this one is in joule per mole per Kelvin, and ln. So let's substitute the strain rate, which is 1 10 to minus 3, like that is in hour, okay? And minus ln, what is that? Is 4.5 10 to minus 3. Okay, so that will give you the unit of hour. Let's see whether we need to do something on that. Okay, so that's in the hour. So let me just finish writing all the things down, then we'll check the unit. So that for the bottom 1 over T2 is here, 353 minus, okay, this one 343 T1 is here. Okay, so for a standard, I would say for a standard SI unit, we should use second, okay, second as the unit which we can put here. So it looks like this is the in hour. So if we change that to second, that's per hour. We need to change per second. What's that? The relationship, because 1 hour is equal to 3,600 seconds. So basically per hour, let's say per hour is equal to per 3,600 seconds. Okay, so that gives you 1 over that second minus 1. So I think a right way to do that is you change that unit as well, and then plug that into here, the formula. Okay, because in that way you will make sure all your unit is SI unit. That make sure your answer is right. Okay, so I will double check that. I'm sure this is, otherwise hour is not the standard unit. You wouldn't get a correct answer. And that should give you the answer here. Okay, so let me come out of the screen, and I think the final answer, we haven't finished the final answer. Let's just make use of the limit space here. The final answer, let's write step 3 is find the TR, time to failure, which, like I said before, is the final failure strain over the creep strain rate. Okay, so one thing I think I forget, which is we found Q already, but we haven't found A, right? So in this equation, let's find A, because find A is much easier, because we have 2 equations. We work out the Q, and to get A, we just need to substitute the value into one equation, and also with the Q, then we can work out A. Okay, so A is basically just take only one equation will give you the answer. The creep strain rate over the stress. Now we need to use the stress. And so let's divide again. Divide this E minus Q RT1. Okay. So for the stress is 5 megapascal. For the other things, especially the Q, make sure if you calculate is a kilojoule, you need to make sure you put that into joule. Then make sure the unit is the right unit. Okay, so I don't have enough space here. So let me move these things out. Okay, good. So I think I'm not going to plug in everything here because they are relatively the same. The thing is you need to make sure the unit is consistent. Okay, that's the answer. Okay, let me finish the number 3, which is this part. So once you get A, then you will able to get the whole equation for the strain rate, which let's go to here. So we know A, we tick that. We know the activation energy, we tick that. So basically, if you ask me time to failure and the stress equal to 2 megapascal and this temperature, so I will tell you the answer, which let's say epsilon stress in service will give us all the things we know. But just be careful, the T here is 3, T is 3, which is this value, or TS, yeah, TS, let's make it consistent, TS is a T. So in this case, we will work out the value will equal to a certain value here. Let me find the value. So A here, A is 2.23 times 10 to 11. Okay, and epsilon SR will give you the value 1.066 10 to minus 6. Okay, so that will give me, this is in per hour actually. So I need to correct myself a bit, which I guess someone is wanting to say something or not. If you want to say something, you can say it. Otherwise, can you mute yourself? So I think I need to correct myself. I guess for this kind of case, A, the unit here, A, is already considering the steady state rate in a value of per hour. So A, actually I don't have a unit for that, but that will cancel out all the things, including the stress or strain rate. So that's why from my answer I saw it is when you calculate that, plugging in here without changing these things to per second, you will get this. Okay, we need double check that anyway. So in the revision class, I will make sure this is clear. Okay, I will check that value as well as soon as I finish the lecture. I will see what's going on here. And now once you get this value, the TR basically is this equation SR. So it's 0.1 over that. the blah blah things here. I don't have enough space, but that gives me a lot of a long value hours. Okay, you normally you change that to years. That's 10 to 7 years. Okay, that's the answer for these questions. So let's have a break now, and I will figure out what's going on here and check this value. So have a 10-minute break. You can just relax without quit the session. Okay. Any questions you can ask now. Okay, someone say A is wrong if you would like to check. Okay, to answer the questions, the grade for course of 1 will be released. I think I can release after today. It's all done. And just because I need to check, is there any mistake from the markers? I did remark some of the coursework because I think I should give a bit more point. Some of the markers, sometimes they didn't understand the questions very well or very well. They just mark against the mark scheme. So actually, the kind of have some time. Sometimes they will get just give you a bit 1 point less. So I'm not going to do that for each of you, but I only check the one who got very low marks. So I try to encourage to have a bit more marks. So I think after that I will release the grading. I think most of you are doing very well. I can see a lot of people got full marks. And the only thing I would say is when you look at the mark is now scaled to 100 rather than 40 because that's the system that asked me to put the full mark to be 100. So I have scaled all of your score to 100. So it looks better. So everyone, if you're doing well, you'll get 100. Okay. Let me just turn off my heater. It's very warm here. Just a second. Okay, let's come back. I just want to make some clarification. I did check the calculation and I found there's some mistake here. Let's go back to this slide. Can everyone see me? Let me just double check. I think I didn't. I think, yeah, it's still here. Okay, good. Now, so let's come back to the questions. Like I just said, whether we should convert the unit from per hour to per second, the answer is no, we don't need to do that. Just keep it, okay? And the reason for that, I think, is because for the unit in the equation, they will eventually cancel out because the constant a, we are considering this unit, okay? And I did check this q. If we don't convert that to per second, the answer from this part will give me the answer here. So that's correct. But I did check A. The calculation here is wrong. Okay. That's why someone said A is wrong. I thank you for reminding me. I did check it. And let me showing you the right answer. I did that in the Excel and I found is 1.4 10 to 19. So the answer here, let me find my pen. So the answer is 1.4 10 to 19. Okay, just forget about this part and this part. And when you plug in this value to this equation, the final answer is right. Fortunately, actually, final answer is right. That's why someone said he plugged in these things and didn't get this answer because A is wrong before. Okay, now we are clear to ourselves. So don't need to change the unit first of all, and just using per hour. And in the end, you will get the answer in hours. And you see actually about 10 years. That's not bad value for this replacing knee joint. So you can wait for 10 years to change it. Someone ask questions again. Let me going back. Thanks. Good. Nice. So let's go. So here is the it's a better version of this answer, but be careful. I think I need change this part. So 1.41 10 to 19. Okay. For the other things, it's right. Now we finish the example, and then let's talk about the creep mechanism. So if you know the macroscopic behavior of the creep, but you don't know why it has that creep behaviors. So for engineer, or especially you are from this mechanical engineer or material science, you need to explain well what's happening in micro scale for the structure, what's going on high temperature. And here, let's just discuss it. So the equation we already know is this part. And it depends on the high stress, high temperature, these two. So also the activation energy basically is a constant for certain material. A is a constant for certain material. N is a constant as well. So the best things actually to explain the creep behavior is to visualize that. By that I mean you need to plot some type of map or curve to help people visualize what's going on for the creep and the different temperature, different time, temperature and stress. So that's our variables. And what's going on for the strain rate and the creep. So there's a very good map which can summarize all of this mechanism. So let's just do that one by one. So here is the deformation mechanism maps. So I'm plotting normalized shear stress. By that I mean you plot the shear stress, you know, shear stress, because for a certain material, you apply uniaxial stress, but actually you will generate a shear stress at 45 degrees. That gives you the maximum shear stress. So you can quantify them or related your uniaxial normal stress to the shear stress, because the shear stress will basically governing the plastic deformation of the material, especially metal. So to quantify that, and we normalize that shear stress against shear modulus. So if you remember, theoretical strength of a material is normally about 10% of your modulus that characterize the atomic bond. Okay, these two atoms, or you can think about there's a bond between the two atoms. Okay, the covalent bond will give you the modulus and the strength. So the theoretic strength is 10%, roughly just below this 10%, 0.1. Okay, and if you look at the shear yield strength, which once the shear stress reach the shear yield strength, tau ys, which can again related to your uniaxial stress, which is about 1 over square root 3 of uniaxial tensor yield strengths. You can go back to our previous lecture. You can find this relationship. So at this point, you will reach the plastic deformation. So above that, the whole area here is going plastic deformation, considering you have some strain hardening. So the material is still going very strong if you keep apply strain. So you can assume this whole area is plastic deformation. Okay? But come back if you're below this shear yield stress, and you will have this elastic deformation. Okay? The material doesn't fail if you release the load. It can't come back. And in the right axis, in the horizontal axis, we are plotting the normalized temperature T over the melting temperature, that homologous temperature, which cannot define how high is your temperature. So for example, 1 means very high. The material will melt just like a liquid or fluid. That's like very hot liquid, I would say. So that's very high temperature. If it is 0, okay, that's very low temperature, freezing or something happens, and 0.1, they are basically very low temperature. Normally, creep will happen around 0.3, right? So this basically the frame of deformation mechanism maps. And let's look at some special region. Yes, like I said, plastic deformation basically is governed by the dislocation of the material. Doesn't matter of your temperature, right? Whatever the temperature is already reached the plastic yield region, governing by the dislocation slip. I will approach location later on, so you will understand dislocation better. And in some of the region here, when you're under very high temperature, the material almost like liquid. So whatever you have some crack or some damage, they will tend to recover because they're melting each other and form a new bond. So that's the area for dynamic recovery around here, on the high stress to facilitate this dynamic recovery. Oh, this is not, just forget that, because initially I wanted to have a break after that. But now let's look at the microstructure of the metallic material. So we will go back to the mechanism map, and we will fill the map here. There's a lot of different regions we can look at. Okay? Microstructure of metallic material. So if you look at metal in atom level, they are basically have different like lattice structure. If you remember, this kind of face-centered cubic lattice. So you can see the atom here. That's the center on the face. There was also like a body center. So if you look at symmetry, there's an atom in the center. That's the center body BCC, and this is the FCC lattice, face-centered cubic. So in each face, there is one atom which is acting as a center. Okay, so that's the structure for a normal metal, one type of metal. And if you look at a bit larger scale, which is grain scale, so what the relationship between the grain scale and atom scale is, if you look at a grain, which I highlight here, this is the 1 grain, which is this solid line here. That's 1 grain. There's a lot of grain here, but inside the grain, this dot, which represent the atoms on the left. Okay, this atom is basically part of the grain. So you can say, actually, the bulk material, I mean a solid material, is basically formed by atoms. That's bulk. And if you look at the solid line, which we say the grain boundary, which is the boundary between different grains. Okay, so there's so many boundaries here, like I draw here. So we can simplify GB. Okay, Great Britain. Okay, that's not Great Britain. That grain boundary. And so if you look at the microstructure, basically that's mimicking this graph. Is each grain, if you polish the metal surface, you can look at this structure. Each grain consists of a million of atoms like that. And the gap here, you can see that's the grain boundary, a big gap actually. Actually, that's facilitated for the atom to travel. But also the atom can travel within a grain. So that is called bulk diffusion. We will approach it. If the atom going in that region, that's the grain boundary diffusion. The atom travels through the channel and go from here to the channel to another grain, something like that. Okay? So that's the microstructure of metallic material. That will govern the final behavior of material and high temperature, high stress, okay, at a certain amount of time. So let's look at diffusion first. If you know the Fick's first law of diffusion, is basically the relationship of the flux of atom pass through a unit area. Diffusion basically, if I have a, let's say a gas, have some gas molecule here, highly concentrated on here, which we say here, this is a source side, okay? And there's a sink side. Basically, the gas will tend to diffuse from the left-hand side to here. So eventually we'll have a more like a uniform gas molecules everywhere. So similarly for the crystal solid, they are doing similar things. They also have this solid atom travel, although they have much more atoms than the gas. So you quantify that by this flux of atom, basically like a velocity of the atom travel within a certain distance. So it is equal to a minus sign. This times the diffusion coefficient here, times the derivative of concentration. So this is the concentration gradient. Okay, so if you see the concentration gradient here is very high, and in that area is 0. Okay, that's very high. Okay, concentration gradient dc over dx. That will kick in our kind of diffusion control the creep. So let's discuss that. So for a diffusion problem, if you have an atom want to diffuse to a new lattice site, like I said, FCC lattice from 1 cubic, okay, to another cubic, okay, another cubic. They need to overcome an energy barrier, which is basically our activation energy, Q. So there's a probability P of an atom having an energy greater than Q, which is this equation. So that looks very similar to the one we saw, like exponential function minus Q over this KBT. So basically, that's really very similar to QRT. I think there must be a relationship between R gas constant to this Boltzmann constant with something else, okay? Because this atom, you just need to change that Joule to mole, okay? You will switch to switch this Boltzmann constant to the R, universal gas constant. So that's how our equation comes from. It's basically a diffusion problem, but this quantify a probability. If you have a Q, that's the material constant. If you have temperature, raise temperature high enough, so RT will be essentially larger than Q. So your probability then will equal to 1, something very high probability to force your atom to travel from one lattice to another lattice. That's the kind of diffusion happens. So that's the equation for it. So let's watch a video to understand the diffusion better. So can you hear it? Yeah. So for if you just forget about the video itself, okay. So this is the gas phase liquid. You can imagine this is some things you drop from yourself to a liquid, and these things will eventually move from left hand side to the right hand side. Okay, like drawing here. Eventually will be distributed uniformly across the area, like that, become a uniform solution. So how about that for a crystal solid? So often you think the solid is very rigid. It's really hard to move an atom. But there's some case, if you raise temperature or stress, it will force the atom to transfer, like the case you'll be seeing in the video. Okay. Okay. So for example here, interstitial diffusion, where you have an atom sitting around here. Okay. And when you heat up the material, it starts to evaporate. Okay, the atom will move around all kinds of places, and there's some scenario where the atom will move from the left to the right to fill the gap between the atom. Okay, even travel all kinds of all kinds of direction, going horizontal or vertical. That's all random. They have equal chance. So this is kind of a institution diffusion, and there's some other type of diffusion which may be kick in, depend on the lattice structures. You will see soon, which is called substitutional diffusion, or we can also call it vacancy diffusion, because if you have a vacancy here without atom, so that's a free space for the atom to move. So once you actually here, you see that the vacancy is available for all directions. Something here, this vacancy here. So once you heat up the material, it starts to vibrate. You can see the material will fill the vacancy from this left to right, and following that, eventually you will see actually your atom will move around just to fill the vacancy. So that pushes the atom to move in a kind of sequence. So that is kind of called vacancy diffusion. So I think that's clear. Just give you the example for the diffusion in different type of diffusion, institution or substitutional diffusion. Okay. So first of all, let's talk about the bulk diffusion. So bulk diffusion basically is the diffusion of atoms or molecules past each other. Remember, I said in a grain. What's going on? I think I need to click the area. Okay. Now I can write. Okay. So in a what's happened? Okay. Where is that? Okay, it's here. Now my pens come back. Okay. So the bulk diffusion is if you have a lot of grain. The bulk diffusion is the atom move around within the grain. Basically, that is the bulk diffusion, and it is follow a fixed force law. Basically, in this case, if you look at the graph here, that's the vacancy for the atom to move. And equally, there is a similar equation which is governed by this probability equation. Activation energy, temperature, and Boltzmann constant is relevant to the universal gas. Okay, so now let's look at the deformation map, where if we look at the diffusion part, there's two types of diffusion. If you look at a condition where you have a very high temperature, okay, for example, close to here, and very low stress. So very low stress is the axis very low because you never reach the yield stress. So which is here. So this part is called the area for bulk diffusion. So for the bulk diffusion, molecules can slide past each other in the direction of stress. For a material like a thermoplastic polymer, if it is over 8 Tg, is a glass transition temperature, it will become like a Newtonian viscous liquid, like a liquid. It can flow. So for that kind of things, the polymer, the creep strain rate is equal to a constant times to this kind of probability of diffusion. So there's no stress play here. It just become like a fluid. Doesn't matter you apply stress, it will just flow. Okay, that's for thermoplastic polymer. But for metal, there's another more things to play. But let's just look at a video. Here, there's no audio. You can just watch it, and I can say something for it. So this animation for the bulk diffusion. So you can see here is several grains. So we will zoom in to see what happens for the atom once you apply a very high temperature and a very low stress. Let's watch that video. Okay. So now let's zoom in. You can see a lattice structure is start to move from right to left to feel the vacancy. If you look actually for the material everywhere, it kind of happens to feel the vacancy. So that's give the idea of the bulk diffusion within a grain. And this graph basically showing what's happening if you apply some stress, okay, and also has that temperature. So the material of a single grain here will deform as the line indicated. Okay, so you can imagine what's happening here is the atom tend to do things like that. So if you this curve looks a bit hard to understand, let me help you. So if you going back, if you apply stress and high temperature, the atoms will accumulate. Most of them are here. They will supply a lot of atom from here. And here, because you elongate your material and there is more gap or empty space for the atom actually to travel from here to here, also to here. Okay, so that's why in macroscopic you will see a shrinkage. If you look at your sample and tension, there's a kind of a contraction, like a Poisson ratio. You can relate it to that. So transversely, it will shrink. So that because the atom, the material will travel to that area. And what I'm plotting here, that we can see eventually this atom to here, and that part will become a empty space, become a vacancy. Okay, so that's why I'm plotting here. Vacancy flux will follow the dashed line, but the atom flux will follow the solid line. Okay, to help you understand that. So the equation for the diffusion controlled creep is basically, the equation is related by this. The creep strain rate is equal to your diffusion flux, which is J, divided by the size of the grain. Okay, and the J, as I showing you before, is the diffusion coefficient times the gradient of concentration. Will again give you the kind of a value of D. This is related to the distance from the source to the sink. Okay, you can think about this is 1 grain, and that's the size of the grain. So that's the way the D plate, and the strain rate is that one, like velocity divided by a displacement, or divided by a length of the material, which is a grain size. So when you look at the equation for the bulk diffusion, you will see there's a constant here, but now there's a d square here, which is d here, and divide 1 more d here. Okay, so that's why you have d squared, and because it still have some relationship with the stress, not like that polymer. So the stress here is a linear relationship. The n power is equal to 1, and the diffusion coefficient is d here. Okay, so my questions here is, what happens if you decrease the grain size? So if you decrease the grain size, because d square is relatively will change much quicker actually. So finally you will see your strain rate and creep will increase very quick. Okay, so that means if you have a smaller grain size, you will have a higher kind of creep strain rate. Okay, so that's why for some near material you would hope the grain size is big. Even just a single grain would be the best, because you will have much larger grain size for the atom to travel. Otherwise, it travel to the grain boundaries is much quicker than travel within the big grain. So that's why you can limit the creep strain rate, make it small. Okay, so increase the D will give you a smaller strain rate. Okay, let me look at the time. So if it is almost 5, then almost 6, we can stop here, but we have 8 minutes. So I think I want to finish one more, if you allow me to do it. Okay, just to, this is a kind of continuous story here. So we are looking at the high temperature, low stress give us the bulk diffusion. How about if we have a medium temperature around here? If you see here, around here, and apply still low stress, okay? That is called grain boundary diffusion. So the diffusion will happen through the grain boundary, like I said before. So let's look at that. So if you have a grain boundary, basically means there's a big gap between the atoms, and that will facilitate the atom to move, travel around, go to left or right, or just travel through the channel to anywhere else. So the smaller the grain size, actually the greater the grain boundary volume. You can think about that surface area, because if you this is the one grain, okay, one single grain, there is no grain boundary. If you divide by 2, there is a grain boundary comes here. If you divide by 4, become 4. Now you have much more grain boundaries like that. So the larger the grain boundary gap, the higher the diffusion rate, because if you increase the gap between this grain boundary, okay, between these 2 grains, then the much quicker the atom can travel through this channel like a tube, okay? So this is the sketch of grain boundary diffusion. So on the left-hand side, there's a lot of atom available, and since you heat up the material and the atom try to diffuse through this gap between the grains, so they will travel through the grains, eventually travel to some space, free space like that. So that's the sketch of the grain boundary diffusion. So the concentration of atom here is very high, and it will gradually reduce to here, okay? To here, almost a very small amount for atom, active atom to here. Okay, so if you look at the left-hand side figures, that for a certain material, they have different grain size depend on your material refinement. So for one here, there's a lot of small grains, and 1, 2, 3 until 10, you have a big grains on the here like a hexagonal grains. So my point I want to say is, like I already mentioned, if you make it smaller, the grain smaller, so that means you have a short diffusion path, the D will decrease, so that your strain rate will increase significantly because that D squared, so that you have much quicker creep happens, okay? And for the grain boundary, actually I want to correct myself, that's not right. For the grain boundary diffusion, the equation is even quick because you have another things kicking, which is the gap. The gap between 2 grains, okay, can be related to the distance of the grain in some sort of things if you consider a limited material. So the gap will kind of have a relationship to the D. So eventually we have a cube relationship here, D cube. So that means the grain size will play more significant role into the creep. So that means if you decrease the grain size, definitely you will have much quicker creep strain. So that's why for turbine blade, we often use nickel single crystal material. There is only 1 grain for that material. Whole material is just 1 grain. Okay, so there's no grain boundary at all. So you avoid that to happen. So if you look at this graph, I'm plotting the diffusion coefficient against 1 over temperature. So at high temperature, the diffusion coefficient for the bulk diffusion is this relationship. So high temperature, you have a higher diffusion. Low temperature, which means lower diffusion coefficient. So let's compare these two. One is the bulk diffusion, D, okay, bulk diffusion, and the other is a grain boundary diffusion, DB. So actually, if you compare the curve, actually you will see in high temperature, the bulk diffusion will predominant, will be larger than your grain boundary, high temperature, okay, high T, because on the left is high temperature. And low temperature T, that D, which you can see here, D is below the dB, is D. So you can imagine in low temperature, there's not enough energy to melt the grains. The grain, which consists a lot of atoms, couldn't move freely. However, the atom can try to find a way, like the grain boundary, the big gap, like a channel to move. So in low temperature, the grain boundary movement is quicker, okay? But on the high temperature, the other way. So I think I can stop here, and the next time we will talk about the which is this area, which is the power law creep, which is basically governed by the dislocation behaviors of metal. And you will see the relationship we have talked about this one. We have showing an example to use it with A times sigma n times the E minus Q over RT. That equation is basically for this power law creep, for the dislocation controlled creep, because it's actually dependent on the stress you apply and also the temperature. Okay, so let's stop here. If you have questions now, you can ask me. Okay, we're in good time, just within 6. Okay, I saw someone ask. On the high temperature creep slide got a bit confused. Okay, so you're talking about the one, is creep rate same as the diffusion? Let's look at that, okay? Is creep rate, the creep rate, okay. Yeah, I understand you are saying, you're asking what happens if for the high temperature, why the bulk diffusion is higher than the grain boundary diffusion, right? So the creep strain rate, let's think about that. So let's assume the creep strain rate is the same. We are just talking about the diffusion. Diffusion is basically a diffusion parameter, diffusion coefficient, okay? Someone type it, okay? Thanks, okay? And so what I mean is, let me draw that as well. If you are in a high temperature, the grain, for example here, like that, you have a lot of atoms. Their high temperature, very high, so they are almost like a fluid. The grain is relatively free to move. So even within a single grain, the material is move very fast. So there's no need actually to travel through the gap between this grain. So even within the grain, the diffusion is very quick, okay? And that's why for this curve telling us the D, bulk diffusion, is larger than the diffusion coefficients in the grain boundary. That's when high temperature. The material, you can imagine, is like a fluid. So you don't need to consider the grain. In most of the case, you can imagine the fluid like a metal, they will almost melt. So there's a lot of grain will melt to a single grain, something like that. So even in that case, there is not so many grain boundary available for that case. Okay, so there's another answer for it. Let me know if you still can